Hi, in this video we're going to learn about buffers. A buffer solution is an aqueous solution that contains both an acid and its conjugate base. And the reason that buffers are so important is that they can resist changes in pH. Later in this video we'll talk more about how we can actually quantify how much buffers resist changes in pH, but for now we're just going to think about it qualitatively. So to illustrate how buffers can resist changes in pH, I'm going to use an example system that is important both from a biological point of view and an environmental point of view, and that is the carbonate-bicarbonate buffer system. So carbonic acid is a polyprotic acid, and in this particular case, we aren't actually using carbonic acid, we're using its first conjugate base as the acid, and then the second conjugate base as the conjugate base, if that makes sense. So carbonic acid only appears in the system at relatively high pH, so that's not what we generally see either in our body or in the environment. Usually we see a mix of carbonate and bicarbonate. Now, when we say that a buffer resists changes in pH, we mean both that it is somewhat resistant to the addition of acid, so the pH won't go down as much if you add acid, and also we mean that it's resistant to changes if you add base, so the pH won't go up as much if you add base. So let's look at how both of those work. So of course, if you have a system which contains a weak acid, it will form an equilibrium between the protonated acid form and the deprotonated acid form, the conjugate base, plus H+. And so if you have a system that contains both, if you add H+ to the system, Le Chatelier's principle tells us that the system will get rid of some of that extra H+ by turning products into reactants, basically turning conjugate base into the protonated acid form. And again, if you think about what happens when you have a conjugate base, that can react with water to form the conjugate acid and OH-. So if you add a whole bunch of OH- to a system, then Le Chatelier's principle tells us that that extra hydroxide will react with our HCO3- to form more conjugate base and water. So in this case, the reversible reactions at equilibrium help take up that extra H+ or OH- that's put into the system. So what we're going to do now is we're going to look at a system that is a buffer system that has both an acid and its conjugate base in the same solution. And if this problem looks familiar, that's because this is the exact same problem that we did when we talked about solutions with common ions, formic acid and sodium formate. So if you remember, we did that the long way by writing out an ice table and calculating the pH, but I'd like to show you a shortcut. Let's take our equation for Ka and let's take the negative log of both sides. So now we have negative log of Ka equals negative log of H+ times A- over Ha. And then we're going to use our log rules. The log of something times something is the log of something plus something. So we're going to separate out the log of H+ from the log of A- over Ha. And we get the negative log of Ka equals the negative log of H+ minus the log of A- over Ha. Now the negative log of Ka is pKa. The negative log of H+ is pH. So we can substitute those in there, and I'm going to shuffle the log of A- over Ha over to the side with pKa, and we get what we call the Henderson-Hasselbalch equation, where pH equals pKa plus the log of A- over Ha. Now we're going to use this two different ways in this video. The first is to calculate the pH of a buffer solution. The second is to help us prepare a buffer solution with a given pH. And that comes in useful if you're working in lab. So let's talk about how to calculate the pH of a buffer solution. The first thing is to find or to calculate the pKa of the weak acid that you're working with. So sometimes you'll have the Ka that you need to convert to pKa. Sometimes you'll have the Kb of the conjugate base, which you need to convert to pKb and then to pKa. But somehow you need to get to the pKa of whatever the acid form is. The second thing you have to do is identify the acid and the conjugate base concentrations. People usually have no trouble finding the acid concentration, but because the conjugate base is usually part of a salt, as we talked about in our last video, sometimes people have a little trouble identifying it. The third thing we do then is once we have our concentrations and the pKa is we plug that info into the Henderson-Hasselbalch equation and get our pH. Here is that same problem again, and we're going to do it with the Henderson-Hasselbalch equation, which goes a lot faster than using an ice table. So we're going to start off by finding or calculating the pKa. So we have the Ka for formic acid. So to calculate the pKa, we're just going to do the negative log of that, and we get 3.77. We've got our pKa. Now let's identify the acid and conjugate base concentrations. Now you notice there are two substances in here. We've got formic acid, which has a concentration of 0.050 molar, and because it says acid, we know that's our HA. And then we have our sodium formate, and so the only thing left for that to be is our conjugate base. That is 0.120 molar. Now we're going to plug those into the Henderson-Hasselbalch equation, where our pH is the pKa plus the log of A minus over HA. So 3.77 for our pKa, log of 0.120 over 0.050, and we get a pH of 4.15. Now if you go back and you look at the other video, I think we got a pH of 4.16. That's probably just a rounding error somewhere. It should come out similar, even using different methods. Okay, here's another buffer problem. This one is a bit different because here we're using ammonia and ammonium chloride. So the thing you can usually find the equilibrium constant for is ammonia, which is a weak base. And so we have the Kb here. And so when we go to find or calculate our pKa, let's start by first doing the pKb, which is the negative log of our Kb, and that will be 4.75. Then we can calculate our pKa because the pKa is 14 minus pKb, and that gives us a pKa for ammonium of 9.25. So now we have our pKa, and now we get to identify the acid and conjugate base concentrations. So we have NH4Cl and NH3. Now NH4Cl, remember, is a salt. It will dissociate into NH4 plus and Cl minus. And so NH4 plus is going to be our acid because that has an extra proton compared to ammonia, NH3. Our HA concentration is going to be 0.252. Our conjugate base concentration, A minus, is going to be 0.157. And now we can plug those concentrations into the Henderson-Hasselbalch equation. And let's just say 9.25 plus the log of 0.157 divided by 0.252 gives us a pH of 9.04. So now what we're going to do is we're going to quantify how much the pH changes if we add an acid or a base to a buffer. So the first thing to do is to just identify what sort of equilibrium we're looking at. Are we adding acid, in which case the acid is reacting with A minus to turn into HA, or are we adding base, in which case the OH minus is going to react with HA to turn it into A minus. Once we've done that, we're going to find or calculate the pKa for our HA, whatever the acid form in the buffer is. Next, we're going to make an ice table. And this is going to be different from previous ice tables because it's only going to show the number of moles of acid and conjugate base. We don't care about H plus, we don't care about OH minus. Those don't go in our Henderson-Hasselbalch equation. Next, we're going to calculate the change, and we're going to assume that all the H plus we add to a solution turns the A minus into HA. All the OH minus we add to a solution turns HA into A minus. And then finally, we're going to take those final number of moles and plug them into the Henderson-Hasselbalch equation to calculate the final pH. Now, you'll notice here that we're using the number of moles and not the molarity. That is because oftentimes when we add acid or add base to a solution, we're going to change the volume, and so concentrations will adjust. It is easier to work with numbers of moles because those represent the actual concentration in the buffer better. Before we start a problem, what I'm going to do is look at what happens if you don't have a buffer solution. So how much does the pH change if you add 0.100 moles of HCl to 1 liter of water? Now at the start we're going to assume that our water is completely neutral, therefore it will have a pH of 7. Now the H plus concentration after you've added the HCl, we've gone up to 0.100 moles in 1 liter of water, and that gives us 0.100 molar H plus. So pH is going to be the negative log of 0.100, and our ending pH will be pH 1. So that's a pretty huge pH change from 7 to 1. So now let's look at a buffer solution, and we're also going to add 0.100 moles of HCl to 1 liter of this solution, and look at how much the pH changes. So in this case, we're adding an acid, so the appropriate reaction is going to be HA, which in the case of this particular buffer solution is HNO2, nitrous acid, in equilibrium with the conjugate base, nitrite ion, plus H plus. And let's find or calculate the pKa. Well, we're given the Ka here. Our pKa is the negative log of that Ka, which is 3.15. So now that we have our pKa, we're going to make an ice table. And again, this is with the number of moles of acid and conjugate base only. We're leaving off the H plus. So we have 0.300 moles of each. Now, before we go on to do the next step, let's look at what the pH of this solution is before adding acid. So the current pH is the pKa plus the log of A minus over HA, which is 3.15 plus the log of 0.3 divided by 0.3, and that's just 3.15. So we're going to hold on to that. For this, we assume that all the H plus we add turns A minus into HA. What this means is for every mole of HCl we add, we're going to lose 1 mole of our conjugate base, nitrite ion, and we're going to gain 1 mole of our acid, nitrous acid. So we're going to lose 0.100 moles in this case of nitrite. We're going to gain 0.100 moles of nitrous acid, and now we can get our equilibrium numbers of moles. Now we're going to take those numbers of moles and we're going to plug them into the Henderson-Hasselbalch equation to calculate our final pH. So our pH is going to be our pKa, 3.15, plus the log of 0.2 divided by 0.4, and that gives us a pH of 2.85. Quick summary, we added 0.100 moles of HCl to a liter of pure water. The pH dropped from 7 to 1, so 6 full pH points. We added the same amount of acid to 1 liter of nitrite buffer. The pH dropped from 3.15 to 2.85, or 0.3 pH points. So that's a huge difference in terms of how much the pH changed. Now I want to imagine a hypothetical scenario. So here's the situation that we just looked at, where we had 0.3 moles of each. We added 0.100 moles of HCl, and here's the pH before and after. 3.15 before, 2.85 after. Now, what would happen if instead of 0.300 moles, we started with 1 whole mole of each? Okay, so again, we're going to add the same amount of acid and calculate our equilibrium numbers of moles, and let's look at the numbers. So before we add the acid, our pH is 3.15 plus the log of 1 over 1, and that ends up being pH 3.15 again. Because when you have equal numbers of acid and conjugate base, your pH is always the pKa. Now, after we added the acid, our pH is going to be 3.15 plus the log of 0.9 divided by 1.1. And that gives us a pH of 3.06. So now look at the difference between our after pHs. When we only had 0.3 moles of acid and conjugate base, it dropped by 0.3 pH points, where if we had a whole mole of acid and conjugate base, the pH dropped by only 0.09 pH points. So the amount of acid and conjugate base we have in our buffer solution matters, even if we start at the same pH. And that is related to something that we call buffer strength, which is the amount of acid a buffer can absorb. The more buffer components you have in solution, the more that buffer can also protect you from pH swings. So finally, we're going to talk about preparing a buffer solution of given pH. Now, there are multiple ways to do this, and I'm starting with a very simplistic one that helps you understand how to think about buffer systems. Basically, we have 3 steps. First, pick the right buffer. So basically, you're looking at the pKa. You're looking for something that has a pH close to the pH that you want your system to be. Next, we use the Henderson-Hasselbalch equation to calculate the ratio between acid and conjugate base. That's the A minus to HA ratio. And then finally, we're going to multiply that ratio by some sort of factor that accounts for the buffer strength that we need. So first of all, how do you pick an acid with a pKa? Well, it's very easy to look at a table of pKa's and just find something that's close to what you want. Let's talk about how to make a buffer. And in this particular case, I picked a pH of 7.8, which is pretty close to the pH of your blood. So that would be a nice biologically relevant buffer pH. So the first step tells us to pick an acid with a pKa within 1 pH unit of our desired pH. So we want 7.8. That means we need to pick something that has a pKa between 6.8 and 8.8. Now there are 3 that qualify on this table. I'm going to scrub out ethylene diamine because we want something that's as close as possible. And so there are 2 that are equally close, 7.53 hypochlorous acid and tris, which is short for tris-hydroxymethylaminoethane. That's actually fairly commonly used for buffers in biology labs. But I'm going to pick hypochlorous acid for this particular thing. Now we need to use the Henderson-Hasselbalch equation to calculate our A minus to HA ratio. And so what we're going to do, we're going to plug in the pH we want, and we're going to plug the pKa of our chosen acid into the Henderson-Hasselbalch equation and solve for the ratio of A minus to HA. So our chosen pH, 7.8, equals our pKa of 7.53 plus the log of A minus over HA, which means the log of our ratio equals 0.27. And now let's get rid of that log by doing 10 to both sides, and we get A minus over HA equals 1.86. So there's our ratio. What does that mean in terms of weighing things out? Well, what you're going to do is you're going to multiply that ratio by an appropriate buffer strength factor. So what does that mean? That ratio tells you the ratio between the number of moles of your conjugate base that you get versus the number of moles of your acid. So for example, you could just multiply it by 1 mole and you get 1.86 moles of NaOCl and 1 mole of HOCl. But that's a lot of moles, right? You also might do 0.186 moles of sodium hypochlorite and 0.01 moles of hypochlorous acid. Or if that's too little, you could do something in between. As long as the ratio is the same, it does not matter what the actual numbers of moles or the actual concentrations are. In conclusion, buffers are really useful in any environment in which pH changes need to be regulated. They're important in our body because if our body gets too acid, our proteins start to denature, and if our body gets too basic, our proteins start to dissociate into their component amino acids. And you can imagine they're also important in places like the ocean, where there's all sorts of animals swimming in there that probably would be very unhappy if it got too acidic or too basic. And so the fact that these buffers exist actually protects life here on Earth. I hope this was helpful, and I will see you again soon.